Right, for last lecture, I forgot something that was totally important to segue into magnetism. Previous to last lecture, we had talked about how a magnetic field will put a force on a moving charge. And it was, I think, Hans Ørsted who discovered that the reverse was true. He was setting up for a physics demonstration. So he's got all this stuff set up here. And he had a cable that was carrying electricity set right beside a compass. And then when he turned on the power through that cable, he saw the compass deflect. And he was like, oh, why would that make the compass deflect? But that was the first understanding that having moving electric charge could create a magnetic field. So last class period, we went through Ampere's law. And of course, yesterday we talked about the Biot-Savart law that explain or that give us equations for the magnetic field strength caused by charge moving. But it's important that we had that first part, and I just totally forgot to mention it, about how it was discovered that you can actually, and I usually actually have a compass out here and a wire so I can turn on the power and you can see, oh, yes, it makes the compass move. But it makes a visible deflection when you have a wire carrying current next to the compass. So another thing that I haven't made clear is this constant, the permeability of free space. Its value is 4 pi times 10 to the minus 7, and I told you I didn't remember the units. Well, now I have them written. Newtons per ampere squared. That comes from a simple way to reproduce. The definition of an ampere is a fundamental unit. Remember, we had kilogram as a fundamental unit, second is a fundamental unit, meter is a fundamental unit. The ampere is a fundamental unit. And the ampere is defined as the current going through two parallel wires that will result in a force of 2 times 10 to the minus 7 newtons per meter between the wires. That's something that could be reproduced anywhere in the world easily. So let's look at this to understand how it works. So I have 2 wires. And I'm going to make the current go up on that one. What direction should I make the current go on the other one? I'll let you decide. Okay, down. So I'll have the current go down on this one. They're both the same current. I is equal to 1 amp exactly. And these are separated by a distance of 1 meter. If these wires are infinitely long, then I can calculate the magnetic field created by a wire. So let's just take the left-hand wire. At the position of the right wire, what direction is the magnetic field due to the left wire? I see somebody was ahead of me already. It's which way?
Into the screen.
Into the screen. So Erin took her right hand, I'm explaining for everyone else in case they didn't follow, took her right hand and put her thumb in the direction of this wire. And then if you wrap your fingers around the wire on this side here, the fingers are going into the screen, hence your answer, into the screen. So I'm going to have a magnetic field that's like that due to wire 1. What's the strength of that magnetic field? You may not have this equation memorized. It's mu watt times current 1 over 2 pi times that separation. I'm just going to put R for the separation. Excuse me?
So it's u watt over 2 pi.
It's U watt I, well, in number, yeah. Okay, so, and then it's, I'll put into, with a unit vector, just say, we got a vector. So that's the magnetic field. Now that I have that magnetic field, I can find the force on wire 2 due to the magnetic field caused by wire 1. So now I look at the equation for the force for a wire in a magnetic field, and that equation is equal to I2 L cross B1, right? That's our equation for the force of a wire in a magnetic field. Well, what direction is L cross B? What direction is L in this wire? Let's start with that. In wire 2, what direction is L? It's down. So I have to have my index finger pointing down. And then how do I orient my hand? Middle finger points in, so I need to orient it like this. And my thumb points away. So it's to the right in this case. Make sure I did that right. Down. Yeah. It's always hard because my picture is opposite rotation. What about the angle? What's the angle between the magnetic field and the current? 9 degrees. So that means that this has, okay, I shouldn't have written the right there. I should have made that's equal to I2, L2, B1. And here's where I should have had the right, R-I-G-H. Now, what is L2 here? It's infinity. This is where you start to say, wait a minute, I don't think this works out right. Well, all we do is we divide both sides by L2. So we do force 2, 1, and I'm going to drop the directions now. We have the direction. Divided by L2 is equal to I2 B1 equals I2 mu naught I1 over 2 pi R. So that's going to be and now we see that gives us 2 times 10 to the minus 7 newtons per meter. And so that's why they've defined the current as a fundamental unit, because it's something that you can reproduce anywhere by doing this experiment. So you would set up 2 very long wires. Obviously, you're not going to be infinite length. And in truth, you really only need to have 1 very long wire, and then you can have 1 short wire. And that short wire has the length L2. And then you measure the force on it when you put current through both of them, and you get your calibration. So that's the fundamental unit, which means the coulomb is the derived unit. Since an ampere is a coulomb per second, then the coulomb is an amp second. And so it's a derived unit based on 2 fundamental units. We found that they repel if the currents are going opposite directions. What if they're going the same direction? Attract. So when Caitlin's brother was in this class for their project, what they did was they actually tried to measure the force of attraction and repulsion between wires carrying current. It didn't turn out very well, but it was a good effort. And it was fun because you have these long wires that you can't touch. So now we're going to get into motional EMF. Not emotional, just motional. When something is moving, if you're moving in a magnetic field, there's going to be a force on charges. So if I have a metal conductor, such as the metal rod shown up here, and that metal rod is moving through a magnetic field, then the electrons that are in that rod, if it's a conductor, the electrons are kind of free to move, right? And so as it moves through, there's a force in the electrons that's going to push the electrons to one side of the rod. And so you make that side negative, and what is the other side going to be? Positive, because it lost the electron. And so you're going to set up an electric field in there, and so that electric field is then going to be a uniform electric field, and you can calculate the voltage just by, and this was on your test, if electric field is uniform and parallel to D, then our equation that delta V is equal to minus E dot D gives us that, well, in that problem, we were calculating the electric field. In this case, we just calculate this result. The voltage difference is the electric field dotted with the distance. Since they're parallel, it's electric field times the distance. So you calculate the electric field unless you get the distance. So that's going to set up a voltage difference. So you can do things like, I have an airplane flying through the air. It's going through the Earth's magnetic field. Well, that means you're probably going to have a voltage difference between one tip of the wing and the other tip of the wing. And so depending on how big that is, and I probably will assign a homework problem for you to do that tonight, you may or may not be able to use that to your advantage. You might be able to charge your devices based on that motional EMF, right? We've got to look at the outcome before I can promise. And I'm not going to do it here because I want you to do it in homework. So, hey, look, same thing, just continuing on. This here is simplifying that equation to, since the electric field is minus V cross B, and then you have that cross product of electric field cross with D, then we have, it turns out that the voltage difference is the speed times the magnetic field strength times the length times the sine of the angle between the direction it's... I better check on what that angle is between the velocity and the magnetic field. So, if you have that problem, which, like I said, I'm probably going to give you, that's how you calculate the voltage difference. So as you start to think about this for an airplane, what's the magnetic field from the Earth? Nobody knows? It's about, depends on where you are, but it's about 5 times 10 to the minus 5 Teslas. Say your wingspan is 80 meters. Make it 100 meters just to be friends. That means we're now at about 5 times 10 to the minus third. And then we have the speed. To get up to 1 volt, how fast is it going to have to be traveling? What times 10 to the minus 3 gives you 1? 1,000. So the airplane would have to be traveling about 1,000 meters per second to get 1 volt. That's Mach 3. Most airplanes aren't doing that. Right? You have the right scramjet. Yes, it can do that. But it's unlikely you're going to be able to charge your devices based on that envelope calculation there. Here is, I heard some students talking about a railgun. Here is the basic idea of a railgun. It's reversing what we just did. You have a voltage difference that you're going to put across a bar. So you're going to make current flow through that bar, and when it's in a magnetic field, then it's going to make a force. And so to analyze this, what you need to know is the current and the magnetic field and the length. So in this problem here, actually, no, I take that back. This is a generator. A railgun is the same thing except for you have a power supply where this has the resistor. If you put the power supply here, that's a railgun. But without that power supply there, you put work in to move it, and then that work is going to cause you to have the voltage, and it works to generate. So in this case, you have the rod and you pull it, and so you have your voltage difference. This here is delta V, right, is equal to EMF. Is the electric field dotted to the length. It actually should have a minus sign there, but that's just directional. So you have the velocity you're pulling it crossed with the magnetic field, and then that direction dotted with the length. When you have these things with a cross product and a dot product, you always have to be extra careful that you pay attention to which angle is which, so you don't end up getting the wrong angles in the wrong places. Once you have calculated the voltage difference, the last step, this problem asks, what's the current? Once you calculate the voltage difference, you have a resistor. How do you find the current? Yeah, use Ohm's law. V equals IR, so I is equal to V over R. So to get the volt or the current, then you just take that voltage and divide it by resistance. So this is a type of electric generator. What was happening when you moved that rod? There's a lot of different answers depending on how you're thinking. So I'm not looking for a specific answer, but any correct answer. Brady, you got an answer? Okay. You're going to generate a voltage difference is a correct answer. Thank you for playing along. I'm paying attention. So when you move this, the first thing that I think is you're doing work on it by moving it. Right? You have to apply a force to make it move. And then the energy that you're creating or that you're putting into it, you're not creating it, is being converted into electrical energy. And that's what a generator does. So this brings us to Michael Faraday. Michael Faraday, one of those many geniuses of physics gone past, is the person who gave us an equation to allow us to calculate for any situation what the induced voltage is going to be if we make something move in a magnetic field. And so I guess I better ask this question before we get started. This, of course, relates to what we just said. Where does the electric energy come from in that problem? Waiting on wood. Okay. We have 05013. And Katie Dieter, what was your answer and your reasoning?
I chose B because the rest, I know it's not a resistor because resistors don't necessarily store charge, and free energy was not likely, can't create energy, and work done, I just wasn't seeing how.
Okay. The correct answer was the work done to move the rod. The magnetic field, there is energy stored in the magnetic field, but it was the work that you were doing by pulling the rod, that energy was converted into making the current flow or making the voltage difference, whichever way you want to look at it. You're absolutely right. There is no such thing as free energy. You will find places on the internet that will tell you about free energy and how to make your own device to capture and use free energy and sell that free energy, but they're bogus. And you're right that resistors cannot store energy. Resistors can only dissipate energy. Okay, so it comes from the work done to move the rod. So this is an example of what happens to lead us into Faraday's law. If I have this loop of metals, that's a metal loop with dimensions A, B, C, D, a rectangle, or a square actually. Initially, it's a no magnetic field, and then you move it into a magnetic field. When I move it into a magnetic field, the electrons are going to have a force to make them move in that wire that moved into the magnetic field. And that force is going to be using V cross B. Well, they're electrons, so you're going to have to put the minus in the end. But using V cross B, my V is this way, the B is into the board, my thumb points up. Because they're electrons, that means the force of the electrons is down, or positive charge goes in the direction my thumb is. Since no positive charge moves, it's not literally accurate, but if you talk about current, my thumb is pointing the direction the current will be. So it's going to make a current that flows up on the side C when we're in position that is labeled 2 in there. So I'm going to have here a current that goes like that. What about the side piece? The top and bottom, those two pieces on top and bottom. Are those going to cause any current? No, why not? Yeah, it's trying to make a current go this direction when their wires are going this direction, so it's not going to cause a current. But because that's a loop, what's going to happen to this current? It's going to go around a loop. So it's going to go around like this. So I'm going to have a current like that. Now, what about in position 3? What's happening? The net result is nothing because I have a current here and a current here that are equal in magnitude but opposite in direction, right? Because they're going against each other. So what's your total current going to be there? 0. What about in position 4? Now you only have one current again, and it's going to be going like this. And in position 5, there's no changing magnetic field, no current. So Michael Faraday took this and recognized that there must be something that has to do with magnetic field changing or motion, and he came up with, okay, where is it? Where is it? I swear I got to have Faraday's law of induction somewhere. I don't think I have it in here. Okay, here's Faraday's law of induction. I had to go a long ways to get there. Faraday's law of induction says that the induced EMF what does EMF stand for? Electromotive force. It's an anachronistic term. What it means is the voltage that's produced is equal to minus delta phi sub B over delta T. Well, we have to unwrap that. We have to understand what it is, or it's useless to us, right? Knowing an equation isn't very valuable. Knowing what it means and how to use it, that's where the value is. So, this thing here is the magnetic flux in units of Webers. I always have to point that out, even though my last name's Webb, not Weber. You do know that the next space telescope is the Webb Space Telescope, right? Because the first administrator of NASA was James Webb. No relation as far as I know, but it's important to have that out there. So magnetic flux. We've already talked about electric flux. What was electric flux? Electric field going through a surface. Magnetic flux then must be magnetic field going through the surface. So the magnetic flux is calculated by the magnetic field. Now this has a perpendicular sign, perpendicular to the area. But we write this as B dot A. And how does that work out? The direction of the area is defined as normal to the surface. And this here was using that perpendicular sign to say, well, we want the magnetic field that's in the direction normal to the surface. So it's the magnetic field dotted to the area, or B times A times, this has cosine of the angle between the surface and the field, or sine of the angle between the area and the magnetic field. Boy, is that confusing, right? You have to make sure you're clear on what your angle is and what you're measuring the angle between. So when you look at a problem like this, make sure you sit back and think, how much is going through the surface? And when you think about how much is going through the surface, then you can make your life easier. In general, we always define this as B dot A is equal to BA sine, and I'm going to put phi, where phi is the angle between B and normal to surface. That has clear words, so you won't have a mistake. Because, the fact that you see sine or cosine, depending on which equation you look at, it's really confusing. So the magnetic flux is the magnetic field going through a surface. One thing this does not have is a closed surface. It's not a closed volume. It's the area that's inside of a loop. So I have a loop of wire. Take, for instance, this loop right here. This loop of wire has an area inside it, this area here. The direction for that is coming out. And so if I take this, the flux going through this would be the area of the circle multiplied by the strength of the magnetic field multiplied by sine of the angle between the direction my finger's pointing going out of the surface and the magnetic field. So that's what we're doing for the magnetic flux here. It's a little bit different calculation because with Gauss's law, we were doing a closed surface. Then we have divided by time. There's a second equation that is equivalent, but it has a capital N out front. That capital N is saying, well, what if I have multiple loops? If I had two loops, and of course they're tied together, so it'd actually be a wire wrapped around in two loops. Then I'm going to have basically one loop plus a second loop giving me double the amount. And if I made a third, I'd have 3 times the amount. And so that's what that N out front is for. You will see this written this way here as a complete equation, or this way here. The upper way is assuming that you're going to take into account the number of loops in calculation of your flux. The lower way is you just took one loop for the flux and then you multiply it by N. Now there's something else here that is of significant importance. That minus sign. That minus sign is to direct us to Lenz's law. Lenz's law is a law to help us understand which direction the EMF is. So I don't have Lenz's law on the next slide like I thought I did. I will just describe Lenz's law. Sorry. So Lenz's law says that the induced EMF will be in the direction that would make a current flow to oppose the change in flux. So if we take an example like we did before, I have this ring and right now there's no magnetic field. If I move it over here and in this region there's a magnetic field pointing that direction, the magnetic flux went from 0 to something that's not 0. To oppose it, I would need something to make it come closer to 0, right? And so what direction should the magnetic field be to oppose that? If the magnetic field is pointing this way, it's going to have an induced magnetic field that's that way, opposite direction, because it increased. Now with this, we have our third right-hand rule. If we have, I didn't go through this last class period, but now we will. If we have a solenoid or a loop with current, we can use the right-hand rule number 2. Put your thumb in the direction the current's going, wrap your fingers, it tells you the direction of the magnetic field. So like if the current's going up here, the magnetic field is going toward me in the center. But if I go all the way around, you see no matter where I am, it's always going to be pointing toward me in the center. And it's going to be pointing away from me in the outside. The third right-hand rule is to take your right hand and wrap your fingers in the direction the current is going in the loop. So if I wrap my fingers in the direction the current is going, my thumb points the direction of the magnetic field in the center of the loop. And so for Lenz's law, that's clearly the easy way to do it. If the magnetic field, if it goes from zero magnetic field to a magnetic field like this, then the induced magnetic field has to be in the opposite direction, so it has to be like this. Put my thumb this direction, and it's got to be going that direction, which from my perspective is counterclockwise, and from your perspective is clockwise. So that's what Lenz's law is. It's a law that tells us the direction that current is going to flow due to that induced EMF. And since you know the current goes out of positive and into negative, that allows us to set up a virtual battery based on that. But here's the thing about Lenz's law. I've said, let's go back 7 slides or whatever it was. More than 7. Okay, so I did this situation of going from position 1 to position, well, let's go to position 2. Because you had a change in flux going from position 1 to position 2. And actually, it's continuing on until you get to the edge being right here. Your flux is increasing in the direction it's going into the slide. So using Lenz's law, if the magnetic field is into the slide, what direction should the induced magnetic field be? Out of the slide, if the flux was increasing. So I need to have my magnetic field out, so I put my fingers like this. Now let's look over here. The magnetic field is still into the slide. But what's happening to the strength of the magnetic field? It's decreasing. So what direction is the flux changing? It's changing in the outward direction because it's getting weaker in the inward direction. So that means my induced EMF is trying to maintain the status quo. And so since the magnetic field is getting weaker, the induced EMF is going to supplement the magnetic field here. And so the induced EMF, according to Lenz's law, is going to be pointing into it, and that gives me that direction. So if the magnetic field is getting stronger, Lenz's law says your induced magnetic field is going to oppose it. If the magnetic field is getting weaker, Lenz's law says then it's going to supplement the strength. Now let's go ahead and go to that clicker question I've skipped over 3 or 4 times. What had to occur for an EMF to form in a wire within a constant magnetic field? Well, no, you haven't answered yet. Okay. Now we'll see if it really is you. No, it's not. 0, 4, 13, 0, 1, 0, 0. I need to shuffle these more because these two, I think, came right back to back last time as well. Caitlin MacArthur. What'd you choose? Okay, why?
It has to be either parallel or perpendicular is my reasoning. I don't know how to explain it.
Well, let's go back a couple slides here. We had the induced electric field was V cross B. So if we're going to induce an electric field, well, minus, of course. If we're going to induce an electric field, what direction do we have to have for our velocity? Has to be perpendicular, because remember that cross product means we're multiple perpendicular parts. And so that's our key there. We're going to have the velocity perpendicular to the magnetic field to induce that electric field, which in turn then produces the EMF, the voltage difference. Here's an electric generator. Now that we have Faraday's law of induction, we know that the induced EMF is minus N change in magnetic flux over change in time. We have here two permanent magnets creating a magnetic field. What direction should the magnetic field be going? Out of what and into what? Out of north and into south. So in the region where that little loop is, the magnetic field is pointing like this. Now this is designed so it looks exactly like an electric motor. The difference between an electric motor and a generator is with a generator, you're putting work in to make it rotate. And then that's going to generate electricity. Whereas an electric motor, you're putting electricity in, and that makes it rotate, producing mechanical energy. So if we look at this, you notice this is a single loop. So N is 1 here. And then I have my area, my flux. Right now, how much flux is going through that loop? None. Because the area is pointing up and the magnetic field is pointing to the side. So right now, there's no flux. But this doesn't ask about the flux. It asks about the change in flux. Right? It's change in flux over change in time. So the flux, N is 1 here. So I'm going to put 1. The flux is magnetic field times the area times sine of the angle between them. And so I have the change in that divided by the change in time. Now, if I have something that's making this rotate at a uniform rate, say I went to visit my parents in the Philippines. My parents should be in the Philippines now. They flew out at 12:20 a.m. this morning. Actually, no, they're not, because that's 12:20 California time. They're still in the air on the way to the Philippines right now. But I went to visit my parents in the Philippines when they were living there, and they had a little hydroelectric power plant. And they had water going through a pipe about this big, not a lot, flowing through and turning a paddle wheel that's supposed to rotate 60 times a second. Now, as you might guess, with only that much water through, when a refrigerator turns on, it puts resistance on that paddle wheel because it needs more work done, and it slows down. So their clocks lost like an hour a day because whenever something turned on, it would slow down. Anyway, so let us assume that we're not working with something that's so iffy that we have a very constant rate. We can say theta is equal to omega t, where omega is our angular frequency. And for our power that's here, we have a frequency of 60 hertz. And so omega is just, omega is 2 pi f, so 2 pi times 60 hertz. If that's the case, then my EMF is equal to -1. Magnetic field's a constant here because I have a fixed magnet. Area is a constant because it's a fixed shape for the loop. The change in sine of omega t over change in time. If I draw a sine curve, sine wave starts right here. If I draw that sine curve, we see that initially we have a maximum. It's going to reach a peak. It's going to come down. It's going to vary. And if you've taken calculus, you know exactly how it varies. If you've taken calculus, delta sine omega t over delta t is the derivative of sine omega t. So one of my calculus students, what's the derivative of sine of omega t? One more piece. times the derivative of the inside. So we have the minus 1 that was out front, BA, and then we should have minus omega. I didn't hear you say the omega there. Cosine of omega t. Sine, because I thought I heard somebody say, okay, it's not negative, you're right. I thought I heard somebody say that, I assumed it was right. So that is what we get, right? We had to do calculus to actually do that. But that tells us what the EMF is going to be. So writing this out equals minus BA omega cosine of omega t. So the voltage is going to be changing sinusoidally, and the maximum voltage is B times A times omega. What if I had more than one loop? What would it have been? Yep. And so the EMF max is going to be number of loops times magnetic field times area times omega. So how can I make a higher voltage for my generator? I can make it rotate faster, make omega bigger. I can make it have a bigger magnetic field B. I can make it have a bigger area for the loop A, or I can make more turns on it. So this is your fundamental generator. So, okay, this is just going through all the ins and outs of it working. This here, what's different between this and what I just did? There's one difference, ignoring the minus sign. Sine instead of cosine. What difference does that make? It's just where you set your reference point. So fundamentally, there's no difference in the two. It's just where you're setting your reference point. And so in this case here, the measurement of the angle was measured to be 0 when it was like, well, I'm not even going to worry about it. It's just a reference for where you measure angle. And so here's what your voltage is going to look like as a function of time. Now this works fine if we want AC voltage. If we want voltage that's going positive, negative, positive, negative, positive, negative. If we don't want AC voltage, well then we've got some work to do, because to get DC voltage, we need to get rid of the negative. So there's a couple ways of doing that. First, the idea of the split commutator. It says it here somewhere. Split ring commutator. Just like when we were making an electric motor and we had the brushes and the two connections so it would switch, you can do that with the generator as well. And so that would do what we call rectify. Rect means right, so I guess it makes it right. Rectify the voltage, so now it's always positive. Now, if you connected this to your iPhone or whatever, that variation in the voltage would be somewhat troubling, right? So we want to do something to make it stay more constant. Can you think of something that would help us keep that more constant? A capacitor. So usually if we want to take a generator and make a voltage that's a DC voltage, we'll do something like this. So we have the split ring commutator, or you can use a diode bridge to do the same thing and not have it. So here's our generator. And then we're going to put a big Herkin capacitor here. Why do you put that big capacitor? Because when you have a positive voltage, it stores energy. When the voltage goes down, it supplies energy. You put a resistance, whoops. You put a resistor here. So it doesn't have to have the same voltage as your power supply. And you will get out of this, if it's rectified, you'll get something that looks like, so we start at 0, come up, something like that. How much it drops is a function of how big the resistor is and how big the capacitor is, because you have that RC time constant for discharge. And so a bigger capacitor and a bigger resistor will work to make it a better regulated power supply. Better regulated means less wiggle. Of course, the resistor in here is going to dissipate energy, so it's not perfect to dissipate energy because you're throwing some away. Okay, there are more sophisticated things. In your automobile, yes, Mahala.
To rectify it, is it the combination of the capacitor and the resistor, or just the
Well,
capacitor?
no, the only rectification I showed was having a split ring commutator. That's the split ring commutator is going to make it so it's always positive, never going negative. There is another way of doing it using diodes, make a diode bridge, we call it. That will also rectify it. But the rectifying is making it positive. It's the regulation is the term we use for making it so it's more uniform. And so I focused on the wording. So with the regulation, what was your question about the regulation?
Is it the capacitor alone that does it, or the combination of
It's the combination. It's the combination because if you didn't have that resistance, then the capacitor would just dump energy back into the power supply as the voltage drops. So in automobiles, back in the day, you wanted to start that car, you had to come out there with a crank, right? And you turn the engine over. But engines don't turn over easily. And so, there's a certain macho effect of being able to start your car. But to make the car keep running, they had a generator. Something like, oh, come on. One more. You can do it. 2 more, 3 more. Something like this, a generator. And then that generator would produce electricity so you could have sparks to light the gas on fire. And then people said, wait a minute. That generator has the same design as a motor. And so we should be able to use that generator as a starter motor. So all we have to do is just change the connection of wires on it, and we can use it for a starter so you don't have to be out there cranking by hand. Genius, right? So then you have cars that just have a generator slash starter. You start it, use it as a motor, spins it up. Then once it's running, it uses it as a generator to create your charge. But then they got more sophisticated. You obviously have to have a battery to use the starter. And then you're charging the battery with the generator. They said this generator is not the most ideal design. It works, it generates electricity, but it's not the most ideal. And so we now have 2 separate things. One that is a starter motor, that looks just like this, and one that we call an alternator. The difference between an alternator and a generator is actually very fundamental. What's moving in the generator? The loop. In an alternator, you have a ring, and I don't think I have a picture of an alternator, sadly. Nope, no pictures of alternators. Well, in the alternator, you have a ring that has a bunch of little loops on it. So if you look at a picture of an alternator, you'll see out here a bunch of overlapping loops on a ring. And then inside, I'm going to look at a side view now. Inside, you have something that looks like this. And that thing is rotating. And what this thing on the inside is, that's really hard to tell from my picture, is an electromagnet that has north and south. And so it's like you have your fingers here, and as it rotates, you go very quickly from north to south because this was north, this was south, and just in a very tiny rotation, you've gone from north to south. That's making the flux change very rapidly because it's very little rotation to change from magnetic field pointing one direction to pointing the other direction. And then you have the loops that are just above that. They're having the flux change rapidly, inducing an EMF in those little loops around the outside. This is both a more efficient generator and it's more robust because you don't have your loops rotating. Your loops are fixed and stationary. so they're not going to have as much stress on them as if they were the things rotating. And so it's more robust and it is more efficient. But what it won't do is it won't work as a starter motor. So that's what we have today in our cars is alternators. Now, I said I was going to do this at the beginning, but I'm doing it at the end again. How did this thing work? When I put this on here and I connect the power, it's going to create a magnetic field in this rod. The magnetic field goes from 0 to large. Back to 0 again, but let's just focus on the 0 to large. I have a magnetic flux that's increasing in this direction, but I have a ring. What's that ring going to do in response to the changing magnetic flux? It's going to have an induced current to oppose the change. So it's going to have a magnetic field that's downward, make current go this way. And since I have a magnetic field up and magnetic field down, well, yeah, we have north facing north and they repel, and so it's pushed off. And so I had a student ask, does it matter what the metal is? So let's just look real quick at the difference between the two. So this is aluminum. Aluminum is a good conductor. This is copper. Copper is a better conductor. Copper is also more dense. They did about the same, right? I think they did about the same because you have a bigger force here and a bigger weight. And the two counter. What will happen if I put this on that has a cutout so it's not a complete loop? What do you think? Yeah, I heard people say it won't do it. Indeed, it did nothing. Just in case you doubt me, think I'm a liar. And the reason is you can't have a current loop form in this, hence no generation.